Okay, everyone, let's get started. Hang on a sec. All right, so let's get started. Today we will be talking about attention mechanisms, which is kind of an improvement over the recurrent neural networks that we were talking about in the last class. So before I get into today's topic, which will be all on the iPad, I just wanted to mention that over the weekend, your project groups were assigned. All of you should have received emails about that. Unfortunately, some of the groups might still change due to people who dropped or new people that added in. So this will be resolved ideally by the end of today or tomorrow at the latest, but please just monitor your email for any updates on the status of your group. Some of you have already reached out to us, that half your group dropped out or something. So we will fix all of these things shortly. All right, and anything else? Oh, your quiz 1, sorry, is released and it'll be due next Monday. So it's pretty short. It's only 2 questions. It shouldn't take too much time. So yeah, good luck with that. All right, any other admin questions? I also forgot to say that if you just added the class and this is your very first class and you're not yet on Piazza or Gradescope, please email the instructor's account and we will get you all set up. Also, if you are new to the class and you just added in the last couple days, you'll have till this Friday to submit your homework 0 on Gradescope. So please keep that in mind. I'll also post that on Piazza, but many of you are not on Piazza. So this Friday on Gradescope, you need to get added to Gradescope before then, so please send us an email. Okay, any questions on that stuff? Okay, so let's start with today's topic. So we're basically going from RNNs to attention. So what I want to do first is something that I didn't get a chance to do in the last lecture, which is explain how the loss computation, that's an S, works in RNN language models. So we talked about the recurrent neural network language model, which predicts the next word at every time step and operates left to right over a long sequence. The next thing we're going to discuss is some issues with the recurrent neural network. So there are 2 main issues. So the first is that there's what's called a bottleneck effect, where in a recurrent neural network you force the information about your prefix to be encoded into a single vector, which is the last hidden state of the RNN. And this might not necessarily be reasonable, especially if you have very long sequences. It's hard to imagine encoding all of the important semantic and syntactic information about that prefix into one vector. The second issue with the RNN is more practical. It just cannot be parallelized across time steps. So this means that every time step, the h sub n depends on the previous time steps representation, right? H sub n minus 1. So I have to compute all of these in sequence. This becomes prohibitively expensive when you have very long sequences and large, very deep recurrent models. So there should be a way to do better than this and avoid both of these problems, and that's the motivation for what we're talking about today with the attention mechanism. So 3 will be, in particular, we'll talk about something called self-attention. In previous years, I have discussed attention more generally as a mechanism that you can apply to a recurrent neural network or to any other architecture, but it has been a little confusing because the self-attention mechanism uses its own kind of modules that are separate from other forms of attention. So in this year's class, we will just focus on self-attention and transformers, and hopefully that clears things up for your understanding. I should note that this concept of self-attention and transformers is one of the hardest things to grasp in this class. A lot of the design decisions made in this whole process are kind of hard to explain properly and also hard to understand conceptually when you involve things like multiple examples in a batch and what kind of computations are actually happening. I think in this semester we will also explore this self-attention mechanism through code, probably next week, to give another perspective on how it's actually working and why it's desirable over the other methods of composition that we've seen. Okay, so let's get started with the very first thing on the list, which is the loss computation in RNN language models. So this is nothing too fancy. It is basically what we've seen before, but I just wanted to draw it out to make the point that even RNN LMs can be somewhat efficient in terms of the loss computation across an entire sequence. So remember, in the RNN LM, we started with our now tired prefix, students open there. Each of these had a word embedding, which we called C1, C2, C3. And then in the RNN, you have an initial hidden state, and then you proceed to compute the hidden states of the model sequentially. So this is H sub 1. And remember, we use this WH matrix to transition between hidden states, and we use this WE matrix to project the embeddings into the hidden space. So our process of computing these H sub 1s and H sub 2s and H sub 3 proceeds sequentially like this. And so then we talked in the last class about how, if we wanted to predict the next word, books, we would apply the softmax layer here to predict books. Right? So this would be the softmax layer. And we used the W sub O, right, W output to accomplish this, right? So this is all that we've talked about so far. Yeah.
Just to clarify, that softmax layer would be the size of our vocabulary?
That's right. The softmax layer here at this final time step is projecting H sub 3 into the space of the vocabulary. So you get a vector that's of the size of the vocabulary, you apply the softmax, and you get your probability distribution. Okay, so if I wanted to perform this language modeling computation of predicting the next word at every time step in the sequence, then I could compute a loss at every time step of the sequence, right? And this is how we actually do training in these RNN language models and in the transformer model that we'll see in the next coming lectures. So it would be very inefficient if I had a sequence, students open their books, I had to split the sequence into multiple prefixes, students open there, and for each one, pass it through this RNN, get the last hidden state, and then do the softmax layer, right? One thing that I can easily do is just use these intermediate steps to predict the next word. So for example, I can also put my softmax layer over H sub 2, and in this case, I'm interested in predicting there, right? And in H sub 1, I'm interested in predicting opened. And at H sub 0, where I have no other information, I can still predict the next word, perhaps given the start of sequence token or something like that. We'll just leave that out for now. But in this visualization, now at every single time step, I can actually compute a loss, right? So let's write out what that looks like. The loss at time step 1 is the negative log probability of opened given the prefix. We'll just leave out the conditioning part for the next couple. Log P of there, and L3 is negative log P of books. So I can do this, right, at every time step because H sub 2 has no information about the ground truth next word there, right? That only comes in to the hidden state at the next time step. Therefore, it's perfectly valid for me to put a softmax layer over H sub 2 and predict the next word there. Does that make sense? So you can see that if I have one sequence, I can turn it into many different predictions. I can have one prediction at each time step of whatever the next word is. So this is when we talk about self-supervision, like you can see how powerful this is. For any given sequence, I can turn this into n different classification problems where n is the length of the sequence. Yeah. Yeah, so I'm getting there right now. So we have 3 different loss terms, right? So what do we do after we compute all of these losses? How do we compute one loss that is the one that we actually want to optimize? And so what generally happens is we can compute the loss normalized over all of the different tokens in the sequence or in the batch total. So for this particular example, I would just take the average of these 3 losses, and this forms my final loss. So now it might be interesting to look at the backprop for this network, at least at a visual level. So before we had talked about backprop with just one loss function at the very end of the network, right? But in this case, we have intermediate losses at every single time step of this RNN. So we need to figure out how this affects the gradients that we are computing. So if you just think about the last time step, right, I'm predicting books. So let's use this blue dashed line here. Sorry. Gradient flow. Wow, that's whatever. Okay, so if I compute L3 up here at predicting books, I'm going to backprop into H sub 3. I'm going to backprop this into the word embedding for there. I'm going to backprop here. And note that in the RNN, I'm sharing all of these weight matrices, right? So let me write that out. So here, remember, we're using, damn it. Here we're using WH and WE. So these WHs and WEs are getting their gradient accumulated every single time we use a WH. We're adding to the existing gradient that we've already computed for W sub H. So if I just had this loss at the last time step, it would flow through all the hidden states, all the word embeddings like this. Right? So this is what we've already discussed, how backprop works. You just work your way back. When you have these intermediate losses, it just works the same, except now at this time step, I have to include the contribution from this loss. And I have to include the contribution from this loss. So you can see how the derivatives that you're computing kind of get a little hairier once you have this overall loss function L, which is a function of these intermediate losses at every time step. But you can also see how it helps the gradient flow in the model. At every single time step, you have a new output layer, which is providing some error signal to the model at that time step. So I'm not going to go into the details on how this backprop works for RNNs. You can check out the previous year's videos if you are interested, but it's not really something you need to know in this class. I think here we're going to focus more on getting to the transformer architecture as fast as possible. So any questions about this, having these loss functions at different time steps, and the intuition behind the backprop and accumulating the gradients?
Why would you want to weight all prefix lengths equally?
So the question is why? So in this case, we are weighting all of the tokens in the sequence equally, right? Because there's no weight saying L1 should be higher than L3. You could imagine, some certain words like rare words should maybe be upweighted more than other words. People have tried variants of this. For example, in computer vision, there is something called the focal loss, which upweights like more rare things and downweights frequent things. In general, this doesn't have any effect on the performance of these language models. It's actually quite important to have the prediction at every time step. So even if the word that you're predicting next is very frequent, like the or something like that, the prefix itself is probably not simple at all, right? A prefix could be difficult to model. The semantics might be complicated. There could be long-range dependencies. So, the model is learning at every time step. It's very hard to discern what is an easy and a hard prediction in order to compute some sort of weighted loss terms. But there have been many efforts. None of them are in use right now. Okay, let me check on YouTube. When backpropping the L3 alone, the gradient is accumulated in WE and WH 3 times respectively. Yes, that is correct. And the accumulation is done by just summing the contribution of each term separately. You can look at kind of an RNN, you can unroll it into a feed-forward network, and then the backprop becomes quite simple to derive. But yeah, that's a good question. Oops, okay. All right, so let us then proceed to the next part, which is the problems of the RNN. And I just want to say that this loss computation that we've looked at in RNNs is the exact same method that is used in transformer language models, just the underlying architecture of the model is different. But we will always be computing the loss at every single time step of predicting the next word in the sequence. And our overall loss function for a batch will be this, the normalized loss at each token. So essentially, this is the I should write it out. This is the average negative log likelihood of the ground truth next word over all tokens in the batch. So this is the general purpose loss function for any sort of neural language model. I'm not going to talk about it much anymore, but you should understand this when we get to transformers. This is the exact same loss function that we are using. And backprop and gradient descent are the algorithms that we'll be using. Okay, so let us then continue with the issues of RNNs. And the first one is the bottleneck effect. So let me just copy this thing again. So here's our RNN again. I'll just take out, okay, I guess I won't take out anything. But if you see over here, we have H sub 3, right? H sub 3 is required to encode all of the useful info from the prefix to predict the next word. Right? So h sub 3, like let's think about what we are asking this vector to encode. We are asking it to encode the semantics of the prefix, right? That there are students and they're in the act of opening something and we want to know what they're opening. We're asking it to encode the syntactic construction that we are in and what is the most likely part of speech or syntax of the next word. We're asking it so many different things, and this only gets more complex as the sequence grows longer and longer and longer, right? So we're asking a whole lot from just one low-dimensional dense vector to encode basically everything about the prefix, and this is not really desirable. So let me just make that clear. With long, complex prefixes, this is an unreasonable expectation. So there have been many papers showing that, for instance, if you have a very long prefix that contains multiple long-range dependencies, RNN-LMs are not really good at predicting the next word in those cases. There are many papers that were published before transformers came out. Even if you stack more and more layers of your RNN to have a deep RNN language model, you still run into this issue where you're expecting just too much from just one vector at the end. So there's a good quote that kind of encapsulates this by Ray Mooney, who's a NLP professor at UT Austin. And he said around 2014, I think, that you can't represent the meaning of a sentence in a bleeping vector. So this quote has now become famous, and it's actually kind of unclear to what extent this is true in 2023, but certainly no one is arguing that you can capture all of the different properties of a sentence and encode it into just one single vector. So, this is not true of a sentence. It's certainly not true of a paragraph, certainly not true of an entire book, right? So one of the motivations for what we're going to talk about next is to get around this this unreasonable expectation of forcing all the information that we need into one vector. Okay, I don't know why I was using red font here. Go back to this. So today's topic, the attention mechanism, a way to get around the bottleneck in neural LMs. And intuitively, attention provides a way to access hidden states that are far away. So in the RNN LM, as we've gone through it, you have the single vector h sub n that you're using to predict the next word. The intuition behind attention is that, well, I might have h sub n, but there could be some hidden states well back in the sequence, maybe like H sub 1 or H sub 3, that could be very important to predicting the next word, right? Maybe there's a long-range dependency, or maybe there's some entities that I need to look up in order to predict the next word. So attention gives you a way of not only looking at the very last hidden state that you computed, but also any sort of intermediate or information at the beginning of the sequence that you might want to predict the next word. So I should give you some historical context of the attention mechanism. So it was developed initially for RNNs around 2014. Some people involved are Bada now and Cho. And it was developed for the task specifically of machine translation. So it provided a way for the model to look at previous hidden states of the RNN, not just the last one when making the prediction of the next word. However, we're not going to talk about those initial variants of attention, but we will talk more about what it has kind of morphed into now, which is called self-attention, and is the core module of the transformer language model, which is powering things like ChatGPT and whatever huge language models exist today. So another bit of context about this, it was introduced by a team from Google in 2017, and it's pretty impressive given the pace of the field that we are still using this today. And we'll see when that will change as well. So the difference between self-attention and attention as it was originally developed is that in the first version of attention, you were doing this to look at previous hidden states of the recurrent neural network. So you still had this dependency on you have to compute the previous time steps hidden state before you can compute the next hidden state. Self-attention gives you a way to get around this limitation by removing the dependency between the previous hidden state and the current hidden state. So it basically accomplishes two different things. It reduces the bottleneck effect, and it also is fully parallelizable across time steps. So it was directly introduced to address the two major issues with recurrent neural language models that prevented them from scaling to really huge data sets and huge model sizes. And we now know that huge model sizes and huge data sets are critical to the performance of our language models today. Like ChatGPT could never have been done with a recurrent neural language model for these issues that we've talked about today. All right. And so I should clarify here that what this means is that the hidden state at each time step is independent of previous hidden states. So this is kind of weird because one thing that we know from how humans read is that we certainly read left to right, and we have dependencies between the words that we've just saw and the current word that we're seeing. Transformers don't really work like that. You can't really draw an analogy to how humans are reading. As you will see, it's quite a bizarre process, the fully parallel way that they process text. All right, so let's get started with self-attention then. So I wonder if I can paste this thing again. Oh, I can, okay. So here, I'm just gonna erase a bunch of stuff. I think I can do this properly. Okay, fix this. Okay, so we had this. This was our straightforward RNN LM. And what we want to do in self-attention and in future architectures is to get rid of these dependencies here. These are what makes our model slow and not parallelizable. It also contributes to the bottleneck effect. Like we keep getting a new vector that encodes every possible part of the current prefix. So our goal at a high level is to have something like this where, all right, this again. So we have this, but instead it looks more like this, where you still have these connections, but now to compute H2, you're going to do this, and to compute H3, you're going to do this. So you can see that the dependencies are flowing from the word embedding part of this input rather than the hidden states. There's no more dependencies between the actual hidden states. So this is just for intuition. It's a visualization. This kind of block can be introduced and stacked on top of each other. So, for example, the inputs don't necessarily have to be word embeddings. They could be hidden states from the previous layer that now get fed as input to another self-attention layer. But we'll get into all of that later on. I just want to talk about the basic computations of this self-attention approach first. So let me check if there's any questions. Nope. Any questions over here? Yeah.
Would that lead to any sort of unfair biasing of, say, C1 in that instance, since it's acting on all three hidden states, whereas something like C3 is only on the final?
Yeah, so hang on, let me just, all right, whatever. Yeah, so you said that C1 is contributing to more hidden states than C2 or C3. Could that lead to some bias? The answer is no, because remember, at every single time step, our goal is still to predict the next word opened or there or books, right? So our goal in each of these cases is to have full information about the entire prefix. So we need information about every single word. It just so happens that the first word is always going to be a part of any of these predictions. But as you'll see as we get through this, the computations here, there are weights on each of these connections. So if the model decides, oh, students is not important for this prediction, it can downweight this, this connection here. So it's not always contributing the same amount to every representation. Other questions? Yeah. Yeah, so the question is, how does this scale to a very long prefix? Like, what if we had thousands of words? How does this actually work in practice? The answer is it does work. It scales if you have very large number of parameters and depth in your model. You can also imagine the effect of increasing the depth of the network. So if you have one layer, it might seem a little implausible that it can get access to all of the information from the full prefix. If you start stacking the layers, though, now you have very complex interactions between many different parts of the sequence. And so if you have enough depth, enough representational capacity, and you've trained your network on enough data, the empirical results show that these models can actually predict the next word conditioned on thousands of words of context. And also there's, I'm just talking about the simplest form of self-attention. The one that is used in the transformer, as we'll see later in this, this next week, is what's called as multi-headed self-attention. So you actually have several different ways of looking at the sequence at one particular time step. So there are kind of tricks to help focus on different parts of the sequence that are used. Yeah, you have a follow-up. Oh, no, you can use the same exact model to compute the hidden state at time step 1000 and time step 1. So we'll go through it a little bit. Yeah.
So you're just basically mapping some finite size hidden doesn't supply there is a maximum size that
Then, sorry, there's a maximum size sequence that every.
There's a maximum size prefix.
Yes, that's right. So the question is, if you're doing it this way, does that imply that there's some maximum limit to how many tokens you can have in your input? That is indeed the case. And this limit has been going up for the newer models. So for example, ChatGPT can have a maximum limit of like 8,000 words. The previously state-of-the-art language models like GPT-3 were 4,000 words, and before that it was like 2,000, 1,000. So this is kind of a function of both the model at training, the hyperparameters, it's something that you pick, but also you pick it kind of based on your compute resources. So nowadays the GPUs and TPUs can allow for longer context training. But we'll talk at length about that in a separate lecture. Yeah. Okay, so let me just go through the computations and then it'll become more clear. Okay, so, because I haven't actually explained how this works at all. Let me try to do this again. I don't know what it was doing before. Okay, that was not a good idea. Is this okay? Can people still see this? All right, I guess I'll just do this. Not sure what's happening. All right, so let's continue with this example. Students open there. I'll write it again here because I want to okay, and so here we have our word embeddings, C1, C2, and C3. And now, instead of doing the recurrent updates as I was doing before, I'm instead first going to project each of these word embeddings to 3 different vectors. So we'll use these, we'll use these blue vectors to represent what is called the query. So this is Q1, Q2, and Q3. We will use these green vectors to represent what are called keys. And we'll use these purple vectors to represent what are called as value vectors. So this directly follows from the transformer paper written by Google researchers. This is the formulation of self-attention from their paper. So before getting into more of the computations, let's just talk about what intuitively each of these vectors is supposed to be doing in this computation. So first, let's talk about how you compute them. This should be familiar to all of us. we simply apply a feed-forward layer or linear layer on this matrix vector product, where W sub Q is a weight matrix and C sub 1 is our word embedding, right? So similarly, I can compute K1 like this and B1 like this. So you can see that these are just 3 different projections of our input word embedding, right? Nothing fancy. We have seen this feed-forward layer before in our concat neural language model. So we're calling this one the query, this one the key, and this one the value. So this can be a little difficult conceptually to understand, so I just wanted to give some intuition of these. So the query and key are used to compute what's called an attention score. And we compute this attention score by the dot product. So like Q dot K. So for every single word, you can see that I have a query vector and a key vector. And so what we're going to do is, let's say I want to predict, I want to get the hidden state at time step 3. So I'm going to take the query vector at time step 3, and I'm going to compute the dot product between Q sub 3 and all of the key vectors, K sub 1, K sub 2, and K sub 3. So intuitively, you might think that one of these key vectors that is particularly helpful for predicting the next word, like that position is particularly helpful, might have a high dot product. And a word that is not helpful should have a low dot product. So this query and key are essentially acting as this kind of scoring function to tell you which parts of the sequence should you pay attention to, right? That's why it's called an attention mechanism, intuitively. Now, this value vector is a little harder to explain. I can just tell you what its role is in this whole process, which is these vectors encode the information used to compute the hidden state. So basically, we're using Q and K only to compute scores of like which of these positions do I want to look at the most. And then I'm going to essentially use those scores to weight the value vectors and then take a sum, a weighted sum of all the value vectors using the scores that we computed from the query and key vectors. So all 3 of these vectors are just different views of the input, right? They're different projections of the word embeddings here. They're all playing a role in determining the final hidden state. Yeah. Yeah, sorry. So these weight matrices here, these are weight matrices that are parameters of the model. So intuitively, these weight matrices W sub Q, W sub K, W sub V are trained via backprop. And the whole point is that they're trained such that when you compute the attention scores, the model looks at parts of the prefix that are important when predicting the next word. So that's actually what we're learning, the weights. Yeah.
So the attention score that we calculate for each of these words, would they differ in context of the word that we are trying to predict? As in right now, Q1, K1, and Q2, K2, all 3 are going to be giving 3 different attention scores for this word. But predicting the next word, how much importance each of these words have to be.
Yeah. So the question is like, so let's say I compute the attention scores at one time step. Won't they change when I compute the attention scores at the next time step? They do. And as you'll see, we're using a different query vector at every time step. So at the second time step, we're going to compute the dot product between q sub 2 and the key vectors. At the third time step, we'll compute q sub 3. Yes? So, I mean, it comes from the retrieval literature, right? So the query is kind of like at the current time step, I have some representation of the information that I've seen so far. And I want to know, like, given this information, what previous information can I kind of look up to help with my prediction of the next word? So the keys are kind of encoding how helpful a particular or some information about that position in the sequence that may or may not be helpful to the final prediction. The query is what actually measures whether a particular key is helpful or not. So both of them are kind of used in concert to predict the attention score. If they were the same vector, it would be a little challenging, right? So if you imagine, instead of taking the dot product, I computed like a cosine similarity, and I had the same vector for both the query and the key, then I'm going to upweight myself, the current position, the highest, right? So that basically is one intuition why you might want to split them into two different vectors. That's right. Why don't we? So the Q vector itself is intermediate output from this weight matrix W sub Q, which is one of the parameters of our network, as well as C sub 1, which is a word embedding, which is also a parameter of our network. So those are weights that are trained, and this equation gives us a vector, which is a product of those weights. So it's kind of like an intermediate product from the network.
Are all the W matrices shared across the whole sequence?
This is a good question. So here I've just shown you like 3 different weight matrices, WQ, WK, WV. These are shared for all positions in the sequence at a particular layer. When we get to stacking more layers, you will use different matrices at each layer. But yeah, they should be shared, right? Because although we will talk a little bit later in this lecture about how we include word order into this formulation. Because one thing you might have noticed is that in this formulation, there's no information about the order of the words, right? But you'll see that there is a kind of hacky solution for encoding the word order. Intuitively, it's not anywhere near as pleasing as the recurrent neural network where you have the left to right inductive bias. But let me go through some more of the computations first, which might clear up some of the remaining questions. So let's start from here. So let's assume we have these query key value projections. And just to go back to your point, I'll write out one more so we're all on the same page. So Q2 equals F of WQ-C2. So you can see that this WQ and this WQ are the same. Okay, so the first thing I'm going to show you is computation of hidden state at time step 3. So this is the final time step here. We want to compute a vector that we can use to predict the next word books. So what do we do? Well, I've already told you, and I guess I'll use red for this. I've already told you that we use a query and key vectors to compute these attention scores. So what does that actually mean? So we take the query associated with the third time step here, and we take the dot product between this query and each of the key vectors. So now we get a vector of scores, which is, let me write this, attention scores. We have this vector Q3 dot K1, Q3 dot K2, Q3.K3. And note that these are all dot products, so we have 3 scalar numbers here. So if you recall, we talked about the softmax function before as a way of essentially converting any vector of real valued numbers into a probability distribution. This is another instance where we use the softmax function. So here, we're not using it to predict the distribution over the vocabulary. We're actually just using it to get a distribution over the time steps of this sequence that we've observed so far. So you can actually view the attention score as a probability of, like, how helpful is this time step? How helpful is this time step? How helpful is this time step? Softmax is just normalizing these attention scores. So when we do this, what does this actually look like? So just like we plotted the probability distribution over the next word, here we can plot the probability distribution of the attention score. So Q3K1, Q3K2, Q3K3, and here we might observe, something like this. So 30% on the first time step, 50% on the second time step, and 20% on the third time step, right? The softmax allows us to get this kind of probabilistic interpretation of the attention scores. So now we're all done with the query and the key. Its purpose is satisfied. We have got these attention scores. They're telling us which parts of the sequence are most important for predicting the next word. So the next step is to actually compute the hidden state. And remember, we talked about these value vectors as the ones that are actually used to encode the hidden state. Query and key are only for the scores, the values for the actual content of the hidden state. So if I wanted to compute h sub 3, I'm going to just take a weighted average, a weighted sum of all of the different value vectors, where the weights come from these attention scores. So I can do 0.3 times the first value vector, 0.5 times the second value vector, and 0.2 times third value vector. And here you can see that I have this linear combination of all of the different value vectors where the weights are from these attention scores. And this gives me, finally, my hidden state, h sub 3. And I can pass this hidden state through a softmax layer and predict the next word, books. So these are the computations that are involved at the third time step of this self-attention network. Any questions? All right, let's try this again. Okay, well, all right. So now let's proceed to the second time step where things get just a little bit more interesting than this, although not super interesting. So let's take this and copy it. So here I'm going to do the same thing at the second time step. So I again have this, but now I'm not going to be doing these. And I'll get rid of this. Okay, so here, what I want to do at the second time step is use Q2, right? This is my query. And I want to take the dot product of Q2 and K1 and Q2 and K2. Now, do I actually want to compute the dot product Q2 K3? That's right. So remember, my job at the second time step is to predict the next word, which is there. K3 is a direct function of the word embedding for there. So if I actually predict if I compute Q2 K3, of course the model should want to focus exclusively on K3 because it contains the answer to the problem of what the next word is, right? So I can't look forward because this is essentially cheating. The model will be trivially able to solve this task without any knowledge of the prefix. It has no need to encode the prefix. Does that make sense? Okay. So I'm only, in this case, going to have 2 attention scores that are of interest. So those are Q2 K1 and Q2 K2. And so here I can plot the attention scores again. I can just include this one. So maybe here, in my example here, I have 70% on the first time step and 30% on the second time step and 0% on the third time step because I'll just write it out here. No Q2 K3 because of cheating. So you don't want to look ahead at the actual word that you're trying to predict. So to compute H sub 2, then all I do is the same process as before. I take my attention scores, I average the value vectors, and I use this output to predict the next word there. So you can see that the only difference here is that we somehow want to avoid including the future words in this computation that we have. Okay, so now let's talk about exactly what we have accomplished and how we can compute all of these hidden states in parallel now that we have established the math that we need to get the individual time steps. So the first observation is there are no dependencies between H1, H2, and H3, right? And this is pretty good because in the RNN, this was a critical flaw, right? It made everything have to proceed in sequence. If you look at H sub 3, the computation in no form involves H sub 2, right? It's completely independent of H sub 2. So this means we can parallelize. It also, the other property of this is that we've reduced the bottleneck. And how is that? Well, you can see here that the model does not necessarily have to give a high attention weight to the current time steps vector, right? It could decide to put 100% of the probability on the very first vector. You know, so it has this ability to jump around in the sequence and avoid the bottleneck effect. So in actuality, the meaning of the prefix is just distributed through the entire hidden states of the model. Sorry, in this case, not the hidden states, but the initial input representations. So that's the general idea. Yeah.
In this example, at time step 1, will K3 vector be used to generate the scores?
So here, if we were to do time step 1, we would have only one element in our attention score, which is Q1, K1. All of the other key vectors include the information about the next word, so we can't have those. So the third one also does, right? Because, I mean, yeah, okay, so maybe you could include the third one, but that's not, that's information in the future, right? So it actually could still have information about the second word, yeah. Especially if you stack these in a deep manner, then it's fully contextualized. All right, so I want to talk about how to do this in parallel. So let's take a look at how we can actually compute all the hidden states in just two matrix products. So I'll just rewrite these things like this. So we have the query vectors and we have the key vectors. And we already know like what we want at every time step. So if we write those out, these are just, let's say A1 equals, it's just Q1, K1. A2 equals Q2, K1, Q2, K2. A3 equals Q3, K1, Q3, K2, Q3, K3. So this is our goal, and we want to just get all of these numbers with as few operations as possible. So one thing we can do is just put all of our query vectors into a matrix. So here, the rows of this matrix, each row corresponds to one of the query vectors. And we can put our key vectors into a matrix where each column of this matrix corresponds to one of the key vectors. And now, if we take the matrix product here, our result is this 3 by 3 matrix where you can interpret each element of this matrix as the dot product between the corresponding query and the corresponding key. So you can see that this matrix here contains all of the scores that we actually need for this computation, right? So one matrix product to compute all attention scores. But of course, we're not done, right? Because some of these elements in this matrix we actually don't want. We explicitly don't want, and so we would like to mask them out of the computation. And so that looks something like this. So our desired matrix is something like this, where these cells here at the top right corner are masked. We don't want these to contribute at all to the attention distribution. Could you? No, here the diagonal does not contain any information about the next word. So you are able to include the key vector at the current time step as part of this computation. It's just the ones that come in the future that you don't want. Okay, so how do we accomplish this, and why do we want to do this? These cells have info about the future. Need to exclude these words. So the general process we do this by is called masking. And it is very simple. So let me again paste this matrix. And so remember that one of the usages of this softmax function is to make this into a probability distribution. So we can also apply the softmax here, like row-wise. And what we end up doing is multiplying this matrix of attention scores that we got element-wise with what is called a mask matrix. And so this matrix is 1 in elements where we want to keep the value, and it's -infinity in cells where we want to mask the value. So why would we use -infinity here? Yeah, so remember the softmax function, you're taking e to the value here. So if you exponentiate -infinity, you will get 0. So that's why we are doing this. And so this is obviously very important in this whole process. If you include these terms, then you'll observe your loss goes down very quickly, but it's actually very misleading because you're not learning a language model. So finally, how do we actually get the hidden states? So now at the end of this process, we have obtained the final attention scores, but we still need to get the value vectors, right? So this is also quite straightforward. I'll just draw out an example to show you. So let's say we do this process, we apply the mask, and we get something like this, where these are our attention distributions row-wise, Q1, Q2, Q3, K1, K2, K3. Now, all we have to do to get our final hidden states is to multiply this thing with the value vectors in another matrix. And our final output will give us the hidden states here. So this is basically accomplishing that weighted average of the value vectors. So as you can see, we just computed all three hidden states with just a couple, I think 2 matrix products. So there were no dependencies between H1, H2, H3, which is why we could get to this point where we can just compute the all of them in parallel. And you can see how this is extremely useful, practically speaking, because now you can scale this to very long sequences by just adding more rows to the matrices that you're multiplying. So of course the actual attention computation in transformers is a little bit more hairy than this, because you have batches of different sequences and you also have multiple layers and multiple heads, but we'll talk about all of that next week. One thing that I do want to just end with is going back to the question about word order. Like, this process so far still encodes no word order. So how does the word order component of this work? Let me just copy, let's say, this. I hope this copies well. Oops. So we'll talk about this a little bit more later too, so it's okay if you don't quite grasp it right now. So we had this whole thing here. And essentially the way that this works is to, before you actually start these attention computations, you add another vector to each position of the of the sequence. So the actual input to the model is C1 plus P1, C2 plus P2, C3 plus P3, where these are called positional embeddings. And as intuition, P1 is the same vector for the first position of every sequence, and P2 is the same for every position of, oh, sorry, for going too fast, for the second position of every sequence. and so on. So you might have a sequence that has completely different words than the next sequence, but the position embeddings will always be the same. So the very first position in the sequence, you will add this position embedding to the word embedding and then proceed with this computation. So intuitively, what does this mean? Well, it is giving the model some idea about what position each word in this sequence is at. The position embeddings are learned parameters. Well, I mean, this is actually, they could be either learned or static parameters. In the original transformer, these are static parameters. In the modern transformers, these are learned. And they operate a little bit differently. This is just for intuition that at every single time step, we add some embedding that gives the model an idea of what position in the sequence this word is at. So we'll talk about many different ways to do this later on in the semester. Yes? Yeah, so if you have multiple attention blocks, do you add the position embedding to every block? In the normal transformer, you don't to the input of every block. You just add it at the very beginning. I think in modern models, there have been methods that try adding it in multiple layers or just keeping it at the first layer. It doesn't seem to make a big difference. So most people just keep it at the input. Did you have a question? Yeah. So the position embedding has nothing to do with any sort of linguistic concepts. It's completely agnostic to what word is actually occurring at that position. So you can imagine, regardless of what C1, C2, and C3 is, you will use the same P1, P2, P3 for every single sequence. It's basically just telling the model, at word 1, at position 1, this was the word. At position 2, this was the word, and so on. Yeah?
If you have like multiple attention layers, you don't really need the position embedding, right? Because the hidden vector should contain some information about the ordering of the table.
But you still may not have that order information. If you don't have these positional embeddings, then you don't have any way of, even at the very first layer, encoding that order information. But to your point, there have been several papers that show that if you remove the position embeddings, you can actually get pretty good performance on NLP tasks that are not text generation focused. Text generation, however, requires you to at least know the ordering of the words. So, yeah. Yes.
Just to clarify, is the positioning embedding adds on just a metrics addition on the C1, C2, C3?
Yes.
And
so
does that create any noise? For example, like C1 plus P1 might equal to C2 plus P2. Oh, it's a
sorry. No, in normally it's addition. But like I said, people have explored all sorts of operations. So you can concatenate, you can do some more fancy thing. It seems like simple addition works well. So there is some, I see what you're saying, like maybe it could kind of mess with the word embedding, the content of that embedding. In practice, both of these are trained C1 and P1, so the model can learn how to adapt.
When you predict C4 information from H2?
When you predict C4, do you use information from? No, so you don't use any information of the previous H's for any sort of prediction at future time steps.
Then why don't you just learn H2? Like why would you want to simultaneously have H1?
So we compute H1, H2, and H3 because at each one of those vectors, we're passing it through the softmax layer to predict the next word. So we need to compute every single H vector. That said, H4 has nothing to do with H2 or H1. It's just we need all of the vectors in order to compute the prediction of the next word at every time step.
So you compute the attention scores at one go, and then apply mask. Is there
Yeah, that's a good question. So the question is, can we, instead of doing this masking process, where here we've already computed the dot product of these things that we don't want, so it's kind of a waste, right? And then we're masking them, so we're getting rid of them. It turns out, and we'll look at this in code, that this is much faster than any other approach that computes just the elements you want separately. And this basically takes advantage of the GPU's parallelism to compute this matrix product very quickly, as opposed to doing it all separately.
So if we wanted to add like another attention layer on top, would we compute like a new VK and value query and what was the third one?
Yes.
With a new W for each?
Yes. So I've just shown you the first layer here. If you wanted to put another attention layer over this one, you would have new WQ, WK, WV. You'll compute totally new set of those scores and value vector averages and so on. All right.
Before we make the softmax function, we clarify LMI
Yes. So if you do it after the softmax, then you may not have a valid probability distribution, right? Because if you zero out some terms, then you might not sum to 1, right? So that's why you do it beforehand. Okay, and finally, let me just look at these YouTube questions. Is the output of the softmax a proper probability distribution or a nice way to squash the function? Yes, it is a nice way to squash the function that can be interpreted as a probability distribution. But yeah, you can do it to any vector. Why do the position embeddings need to be learned at all is a good question. In the transformer, they are actually not learned. The original transformer paper, and we'll see that next week. They have a fixed function that gives you some relative indication of where you are in the network. But more modern positional embeddings are actually relative position embeddings, not absolute position embeddings, and they do involve some learned component. There's actually a whole subfield of NLP on just positional embeddings for transformers, so people have tried almost everything. Some are learned, some are not learned. It does slightly affect the performance, but in general, positional embeddings are not like one of the most important aspects of the model. You just need some way to encode position. But we will probably have a lecture later on that focuses much more on all the different methods. All right, so sorry I kept you over time, and see you next week.